It's for modeling things like functional connectivity, Granger causality, looking at statistics across subject populations and trials and such, trying to get at these network dynamics in the brain that we all know and love. It's got a modular architecture, so it's designed to support different modeling approaches. We're going to be going through some of these throughout the different sessions covering SIFT later on. There's an emphasis in the toolbox on techniques like vector autoregression and state space modeling and several novel approaches for visualizing network dynamics across time, frequency, space. The outline of the workshop sessions are as such. So today we're going to cover the theoretical foundations for modeling functional and effective connectivity in the brain using contemporary techniques and legacy techniques. So that means covering things like functional connectivity measures, what's phase locking value, phase amplitude coupling, coherence, then going on to linear dynamical systems and the vector autoregressive model. We're going to learn about the theory behind that, how it works, how you fit these kinds of models, Granger causality and different effective connectivity measures. We're going to cover a range of those. You're going to understand when you come out of this session both the theoretical foundation for Granger causality and causality in general, some understanding of how that's different from correlation or coherence measures and why it's important to use causal models. We're going to talk about scalp dynamics, like modeling network dynamics at the level of the sensor versus the source, and some approaches for source modeling, and then how we adapt to time-varying dynamics in the data, so how we track network dynamics at the time scale of sub-second time scales. We're going to have a practicum at the end on walking through SIFT, so it'll be at about an hour. We're going to do some hands-on work there, and you'll get a feel for the software. So that's today, 2 to 5 p.m. in the Viz Lab. Tomorrow, we're going to move on to more advanced topics, the second set of theoretical foundations. We're going to talk about how we validate our causal models statistically to make sure we fit the data properly. Multivariate versus bivariate analysis approaches for connectivity, how we put constraints, probabilistic constraints in our models so that we can fit larger models, higher dimensional models with smaller amounts of data, and single trial estimation and state space modeling approaches. Also statistical testing will be covered, bootstrapping, phase randomization, group statistics. And we'll conclude by basically an hour of hands-on simulation-based training where we'll be able to play around with using SIFT's rich dynamical simulation package, explore different kinds of models, and also opportunity for you to play around with your own data in that session. It's going to be a bit of a less structured than the walkthrough today. So that's going to be tomorrow, again, 2 to 5 p.m. It's going to be in the INC open space. I've heard that some of you have registered, I think about 50 of you have registered for tomorrow, and maybe 2/3 of that for today. Just FYI, those of you who have only registered for tomorrow, I won't be giving a lot of introductory background. So if you come in tomorrow, that's fine, but unless you already have a fundamental understanding of vector autoregressive modeling, it may be a little bit over your head because we're going to be referring to some of the things from today. That being said, the slides are up there as PDFs, so you can go through the slides tonight, for instance, and it is relatively self-explanatory through the slides in terms of what we're covering in the basic session today. But that's just something to keep in mind in case you're still deciding whether or not to attend today. You're going to get a lot of the meat of the basic foundations today. Okay, just a quick overview of SIFT, just so you get a sense of what the software does and such, and a few fundamental things like the requirements as you're preparing for the modeling sessions. You need EEGLAB, and you need MATLAB 2008A through 2013B. SIFT is not yet upgraded to be compatible with all the new changes that MATLAB introduced in 2000. Actually, this will probably work with 2014A, but changes from 2014B and especially 2015 and later may cause some issues if you're using it from the graphics. You can use it from the command line, but if you're using the graphical interactive tools, you'll run into problems. So that's something that unfortunately you'll need to either pair up with someone who has a version of MATLAB of that sort or grab one before the hands-on sessions. Some of the functions may leverage functions from Signal Processing Toolbox and Statistics Toolbox. It's rare that you'll encounter that. If you have them, great. If you don't, it should be okay. In order to get SIFT, the best way is through the EEGLAB Extension Manager. You could do that now and through my lectures over the next couple hours, just be downloading it. If you've never used the Extension Manager, you can access it through File, Manage EEGLAB Extensions, Data Processing Extensions, and then you just find SIFT and install it. The version you want is 1.4.1. If you get started on that early, it'll be great, because that way we don't have like 50 people all downloading from the network, 80 some megabytes at exactly the same time. So at your pleasure, just download that. It'll also be on USB keys circulating around, but I'd say use the Extension Manager. Okay, just very briefly here, overview of SIFT. As I said, SIFT is a modular toolbox, so there's basically 5 or 6 different modules. Pre-processing, one of the core modules. Dynamical modeling, which includes model fitting and validation and connectivity. Doing statistics on the outputs of those models, visualizing the results. And so that's your typical workflow for a single subject. There's some component of routines for group analysis, hierarchical Bayesian modeling and such. We'll cover a little bit of that. And there's a simulation module that allows you to build sophisticated, reasonably realistic dynamical models of neural activity and project them to the scalp and build basically simulated EEG data under a very wide array of different kinds of network assumptions. So that allows you then to explore different types of modeling approaches with a validated statistical or validated simulation package. The pre-processing routines include a variety of different techniques like detrending your data, downsampling, differencing, normalizing. All the tools are accessed through a GUI. Modeling, different ways to fit your models. We'll go over this today. Different ways to fit your models to the data, probabilistically constrained or unconstrained approaches. So you can choose different modeling approaches. This is a GUI that you use to interact with the modeling tool chain and select things like different optimal model orders, and we'll cover a lot of this throughout our sessions. Validating the model, different ways of testing whether your models fit the data well, whiteness test, consistency, stability. Again, graphical tools help you visualize the results of that and make sense and determine whether your model's fitting the data properly. Connectivity analysis, there's about 15 or 16, I have to count them again, it's been a little while, but a number of different measures for functional and effective connectivity. Pretty much all the ones you typically will find in the research over the last decade can be derived from these kinds of models, so you'll find them here. We'll cover them. And statistics, different ways of doing statistics. Asymptotic analytic estimates, they give you some confidence intervals on different measures. Allows you to look at things like, do I have connectivity that's greater than 0? Or is the connectivity significantly different than some baseline or different between 2 different conditions? These are some of the different kinds of tests that we typically want to apply. Phase randomization allows you to do some tests to see if there's significantly non-zero connectivity, bootstrap, jackknife, cross-validation techniques, and some other Bayesian methods. So we'll cover some of this tomorrow. This is an example of the GUIs that you can use to access those different modeling techniques, and both parametric and non-parametric approaches for statistical modeling. And then visualization, interactive time-frequency grids allow you to view the connectivity data across time, frequency, space, anatomical locations. Interactive 3D causal brain movies allow you to create basically a 3D brain network model or map or view that you can explore and create a movie out of to see how the network dynamics change over time. And a couple other methods that allow you to visualize other aspects of the data. This is how the time frequency grid GUI looks. You can customize a lot of different features. But essentially it produces a plot like this, which is going to be the bread and butter of how you examine the results of your data as you're going through the modeling process. Just to give you a quick taste of this, each pixel here reflects in this case, the causality of the information transfer from a source in the brain here in the column to a source in the brain on the row. And a big red hotspot would indicate that at a given time on the x-axis and at a given frequency on the y-axis, there's a burst of causal flow of information transfer between those 2 sources. So for instance, like here, we can see a theta burst of activity right after pressing a button, in this case making a mistake. between a source in the parietal cortex and a source in the, in this case, in the visual cortex. And so you can click on these and interact with them, and you'll get more in-depth views where you can look at directional information transfer, how one area drives another area. Two areas, one area may drive another area but not be reciprocally driven. So you can separate those out and look at them, the information flow from one area to another separate from the feedback. And this gives you a bit of a richer view. This is the Causal brain movie, just gives you kind of a 3D view of that network dynamics. Here somebody's committing an error, and we see a network emerge here, sort of a stopping network. This is a go-no-go task, actually. Sorry, this is not an error. This is where they're just trying to stop, trying to initiate a, in the go-no-go paradigm, trying to stop. And inhibit a response. I'll skip over this. There's some other ways you can look at the data. Group analysis, as I said, different ways to do group statistics. We'll talk about that. There's a measure projection plugin as well that allows you to look at clusters of like causal outflow across multiple subjects. We'll talk a bit about that. And the multi-view hierarchical Bayesian learning toolchain, which allows you to look at statistical confidence intervals and averages derived in a principled Bayesian way across multiple subjects in the presence of missing data. So if you have dipoles in some subjects and not in another, this tries to make inferences still about what the mean looks like even when you're missing a lot of data. Simulation package, we'll use that quite a lot tomorrow in our walkthroughs, but it, as I said, allows you to generate realistic source dynamics and some nonlinear dynamics as well. For the linear dynamical modeling approach, here's just kind of an example of how you would use it. You've got here you want to create a trivariate coupled oscillator model where you've got three sources interacting, two of them non-stationary. It's a very common kind of thing you see in neural dynamics where areas are not just driving each other persistently, but maybe they're doing it in a burst-like fashion, say, following, say, a theta or a delta oscillation, and sources interact in an oscillatory fashion. So you can construct that kind of a dynamical model here by adding a few lines of code. If it shows, there we go. So you can write out a few lines of code like this and allows you to construct that simulation and ultimately get the simulated data. It's sort of lagging and showing, but there we go. So this allows you to generate this kind of simulated data where you've got bursty-like oscillations and interactions between the different sources. You can create more complex simulations like seizures. And ultimately, you can bypass that whole scripting environment and just use a graphical tool chain to very quickly construct dynamical models where you say, I want to pick these areas in the brain, I'm going to couple them up in this way, generate the dynamics, and project it to the scalp, where now you have basically realistic EEG data that's driven by a reasonably plausible model of the dynamics. And so finally, distribution educational resources here. You go to SIFT Wiki to get access to your documentation and such, and to download the software. You can get it from the plugin manager or Nitrix, as we talked about before. Okay, so that's the Whirlwind Tour. And again, today, session 1, introduction. Tomorrow, we'll deep dive into the more advanced topics, and hope to see you there. Thanks.